So to find the arc distance between the point depicted by, or the point defined by R of A and the point defined by R of B along the corresponding curve, we partition the interval between t equals A and t equals B, and for each sub-partition, for each interval in the partition, we are going to choose the sample point, R of t sub I, represent the distance traveled in that interval by an approximate expression in terms of R prime of t sub I, add those distances up, let the widths of the intervals approach 0, and we obtain finally the integral of R, magnitude of R of t dt, so that our arc length is, again, the sum of our delta S sub i's, which is the sum of magnitude of R of t sub I star magnitude times the delta t sub I, and as t approaches 0, this sum, which is equal to this, approaches the integral from A to B of the magnitude of R of t dt. So we have our arc length formula. The arc length of the curve is the integral of the magnitude of R prime of t dt. If R of t is a function of a vector function, x of ti plus y of tj plus z of tk, then what's the magnitude of R prime of t? Well, R prime of t is just x prime I plus y prime j plus z prime k, where this x prime means x prime of t, y prime of t, z prime of t. And the magnitude of this vector is nothing but the square root of x prime squared plus y prime squared plus z prime squared. Now we'll often write that out, and most textbooks will write this out a little more explicitly, as a square root of dx dt squared plus dy dt squared plus dz dt squared, but it has exactly the same meaning. I'm using the primes to conserve on space, and also because they're easier to write in typewriter fashion. Okay, the arc length is then the integral from A to B of this quantity, square root of x prime squared plus y prime squared plus z prime squared dt. We call this expression the increment of arc length. When we integrate that increment of arc length, we get the total arc length. And we'll calculate that in a minute for a couple of specific functions.